All right, in this video, I'm going to talk about our force diagrams, and I'm going to try something just a little bit different. I took my headphones off. We'll see if the audio quality is any better, different. Still tinkering with systems. I'll look to iteratively improve as I go, and hopefully improve the quality, learn things like editing. But right now, speed is the name of the game, so I'm going to go with the skills that I know how to do. Again, you're always going to get something very genuine from me. It's the stuff that I know how to do and nothing more. So let's get into it. So for our force diagram, I want to work with a system that we've worked with before. So I'm just going to head back to my previous piece, and I'm going to be like, let's copy this thingy. Bam. I love computers. And then we can take this stuff, we can copy this stuff too. So great, now that we have our system schema and just making it a little cleaner, we have our system schema and our picture, we can now draw a force diagram. And the way it works is you can draw a single force diagram for each different object. So I'm going to kind of color code this just a little bit. I'm going to have my cup be red, and if I want to, I could kind of draw my cup like this or draw it on the actual diagram. But one of the reasons why I don't really care to do this just yet is because when we talk about force diagrams, there's sort of two types. There's what we call an extended force diagram. And what the extended force diagram is this kind of a thing, where you kind of draw the object in a way that maybe isn't artistically great, but at least represents what the object looks like. And then you apply the forces at the locations where the forces are applied. There are reasons to do this later, specifically when we start talking about rotation and torque is when we're going to really care about this kind of a thing. Right now, what we're going to do is do the lamer version of this, what I call a point force diagram, where regardless of what the object is, whether it's a cup, it's just a dot. It's just a little object. And if I wanted to draw, I don't know, the plate, so let's do the plate in, maybe yellow's not the best color. I want to do the earth as blue, and I don't need to draw the earth. I don't need to draw it like this huge thing. I'm going to draw the earth as just a dot. And similarly, if I wanted to do the plate is just going to be a dot. I don't need to draw it as a shape of what it actually looks like just yet. We will eventually have a reason to do an extended force diagram, but right now, a point force diagram, which I will refer to as a P.F.D, D as in delta, is what I'm going to draw. Now, I also want to contrast this with other things. Sometimes you'll see people call these like free body diagrams. A free body diagram is typically what we think of as an extended force diagram. I don't like this language and the way that it's done, and I think it's done haphazardly and poorly, so I'm just dispensing with it altogether. But usually they mean this when they mean that, and sometimes they mean this. I'm inventing new language because the old language sucks. So there you have it. But now let's look into the way that this works. If we are building out these force diagrams, let's take, for instance, this cup. We're going to have exactly two forces on this according to our system schema, if we've drawn our system schema correctly. Sometimes we get into it and we realize, wait, there's something impossible, there's something we're missing. But in this case, what we're going to see is one force because of this interaction. The plate is in contact with the cup. That's going to cause us to have a force. The force will describe that piece of that interaction. And similarly, when we look over here, we have another one. For every interaction going into an object, there has to be exactly one force. That's going to be an incredibly useful and important rule, that one-to-one correspondence principle, in terms of helping us create things. I don't know why it's not letting me erase the highlighter, but there we go. Okay. So, if I were drawing the contact interaction from the plate onto the cup, I'm actually not 100% sure how to do that. because I don't really have a good sense for what that contact is. Like I know that the cup is sitting on top of the table or the plate, whatever the thing is, and it's in contact that way. But if we're trying to draw an interaction like it's a force is what we call a vector, which is a type of number that has, or a type of object, I should say. We will have numerical descriptions of them. But it has what we call magnitude, how big something is, and it has direction. So for instance, I could have a vector pointing kind of up and to the right, or I could have something pointing down to the left and it be really big. Those are how we're going to draw these things. And with that in mind, maybe the other interaction makes a little bit more sense to talk about first. If I'm looking at the gravity interacting with the cup, we have this idea, gravity pulls us down. So I'm going to draw it that way. And I'm going to use a little bit of color and some notation to help us really understand what's going on here. I'm going to say that the Earth pulls this down. So this is a force of gravity, and a force is a vector, so it wears a little hat. That vector hat tells us that it's an object with magnitude and direction. And I gave it a specific label. And I can get even more specific if I really want to, saying that this is specifically the description of the interaction that the Earth exerts onto the cup. Great. So now if I'm thinking about the plate interacting through contact onto the cup, well then a description of that interaction probably makes most sense to us if we were just guessing to be equal and opposite. Because we often have this sense that, hey, if I have a force pulling me down, I have to have a force pushing me up, exactly equal and opposite, if the cup's just going to sit there. This is kind of that intuitive version of what we'll describe more of later as Newton's second law, but it's essentially this idea of F equals ma, which is of course an incomplete description for several reasons. A, forces and accelerations are vectors. Mass is a scalar, meaning it just has a magnitude. There's no direction associated with mass. But even this is still an incomplete description because, well, there's more than one force here. We'd have to add up all of the forces. That's what this capital Greek S means, this sigma. Looks like an angry looking E, as it was described by my calc teacher's husband, which I find hilarious and will say all the time. So the angry looking E, the sum of forces equals mass times acceleration. That's kind of this description that we think of as Newton's second law. And we'll get into more about why that is later. But right now, it kind of matches this intuition that if there's something going up and something equal and opposite going down, that it's able to kind of stay at rest, that its acceleration is able to be zero. And if you add up a bunch of things that equal zero, and there is a difference between zero with the vector hat and just the number zero, we'll get into that more later as well. But that's what lets it stay at rest. If it was non-zero, its motion would be changing. It wouldn't be able to be at rest and then stay at rest. To further complete this, I'm going to label this as a contact force. And this is specifically between the plate acting onto the cup. And notice I'm starting to get a little bit lazy. I'm using some color notation, but we'll often not even draw all of these pieces. But I think it's helpful to be transparent while we're learning these things, so we start to notice things that maybe we wouldn't otherwise notice if they weren't pointed out. So that's how this works. For any object I go to, all I have to do is create this thing where I have a one-to-one correspondence between an interaction and the force that describes that interaction. That's how it works on a single object. But now let's go to a different object. Maybe let's talk about the plate. The plate also looks like it has two interactions right now. It has a contact with the cup and a contact with the Earth. So let's think about the contact with the cup first, because we've already kind of looked at the other side of that interaction. So that means this side of the interaction has to be linked with it in some way. This is that idea of what we call Newton's third law, this principle of equal and opposite reaction. That if the plate is pushing onto the cup up, then it absolutely has to be the case that when we draw the contact force of the cup pushing backwards onto the plate. And notice I could switch the order of the letters, but I think it helps us to see the principle at play here, the equal and opposite reaction. When I reverse the arrow, that's all I'm doing. I'm reversing the arrow. However big this one is, has to be how big this one is. That's the equal part. And then the opposite is just, well, this one points down. If the plate pushes the cup up, the cup must push the plate down. Cool. So then let's think about what's happening with our other interaction. If I'm looking at, there we go. If I'm looking at the earth pushing onto the plate, well, then it would kind of make sense to do the same thing that we did earlier, where if the plate was under the cup, that means the earth must be pushing up on the plate. And if we're trying to make everything be balanced, we would draw it like this, where this is the same size as this because of Newton's second law. These two were the same size because of Newton's third law. They were parts of the same interaction. But these are two different interactions. So it's Newton's second law that would make these equal and opposite. At least that's our naive interpretation. We'll get into it in a second why this can't be a correct description of the Earth being in contact with the plate. And the reason is, if we went into this and we measured all of these things, what we would find is that this is actually bigger. Now, why would that be? It's because we're missing something. We're missing something about this plate. This goes back to what we were talking about in the previous video, where we often get into problems and we realize, wait, we've made a mistake, like something is not working out correctly, and it's because we're forgetting an interaction. The plate is also going to have to be pulled down by gravity. There's a gravitational interaction, and we can describe that gravitational interaction. It's interacting with the Earth in two different ways. One is this contact pushing it up, and one is this interaction pulling it down. I'm going to draw this bigger than this just to make a point. They could be the same size if they were, for instance, the same weight, the same mass. We'll get into the differences between mass and weight and why weight is a horrible word and I hate it. But right now, it's enough for us to say a gravitational force acts because the Earth is acting onto the plate. Newton's second law tells us that this force has to equal the sum of these two forces in order to keep this thing at rest. So I might rescale my drawing to make it look more like that. But now we have a more complete description of this object, this plate. And we get to kind of see how this normal force, as we'll eventually start calling it, because it's the normal component of the contact force. Normal meaning not like, oh, it's so typical. Normal just meaning that if this is the surface and this vector points up, that's perpendicular to, which is a synonym of the word normal. That's why we call it a normal force. There will be a parallel component of the contact force later. We'll actually call it friction, but that's a story for another day. Right now, this is helping us to build a more complete description of all of these pieces. And notice it matches our one-to-one correspondence rule. 1, 2, 3 interactions means 1, 2, 3 forces. Exactly. No more, no less. Always exactly 1-to-1. And we'll see that again with the Earth. If we go to the Earth, we would be able to see, okay, for every single one of these interactions, we've already just had a force that describes half of that interaction. So every single interaction here is going to have a third law pair somewhere else. This Earth having contact with the plate, well, that was described with this force here. So that means if the Earth pushes up on the plate must push down on the Earth, and these two vectors have to be the same size because they're linked through that interaction. This is the force of contact that the plate and the Earth, with the plate acting onto the Earth. That means that if I go to, say, the gravitational interaction over here, Well, that has to be the third law pair with this one. If the earth pulls the cup down, that means that the cup must pull the earth up. So I'm going to draw the cup pulling up. Those are linked by Newton's third law. They are equal and opposite descriptions of this interaction on reciprocal objects. Notice, when I have the force of gravity of the cup acting back onto the earth, these two have to be equal and opposite. This one points up, this one points down. It's sort of this flip-flop of roles. The red object applies a red force up on the blue object, which applies a downward force on the red object, and reciprocally goes forth. You fundamentally can't act on another object without it having a reciprocal interaction on you. That's going to be a very common recurring theme that will manifest in a lot of different ways. But we're not quite done. There's still one more. Make some room here. We still need to describe the plate's gravitational interaction onto the Earth. We had an action here, so there has to be an equal opposite reaction. The plate exerts a force up. That is the gravitational force that the plate acts onto the Earth with. We'll get more into specifics with vectors and how to make them mathematical. Right now, everything's in one dimension. It's all along the line, and there's kind of this sense of equal and oppositeness there. But we will eventually have more complicated diagrams where maybe gravity is pulling down and there's some other force going this way. And then we have to figure out other bits and pieces, like maybe we only need a small normal force because this push force has counteracted parts of gravity. We'll get into more of those details. But the basics here that I want us to focus on are the mechanism, the how that we used the system schema to build these force diagrams. We said, okay, for every single force that we want to describe on an object, that force has to describe an interaction. And so we look at a single object, and every single interaction into that object corresponds to exactly one force. When we look at this one, it corresponds to this one. We'll always see that one-to-one correspondence. And if we think about what interactions, how things are interacting, it will always help us to build a correct description and making sure that we know that we're doing things right. We'll be able to check our own answers, check our own work, and find our own mistakes when we follow these sorts of rules. And right now, I'm kind of just handing these rules out. We'll also figure out more experimentally later why these rules have to be the way that they are, why they model it, why it couldn't be something else. We often come into physics with a lot of misconceptions, and we'll really delve into those through careful experimentation and rediscover some of these rules the way that they were discovered in the first place. But those are the basics for force diagrams. This will again come up. Physics is this densely interconnected network of fundamentally interrelated ideas. And so we'll keep revisiting all of these ideas and building more and more complexity as we go through the course.